Hello, my physics students. Today, we're going to continue our discussion on waves, our discussion on sounds, and specifically, we're going to be talking about intensity today. There are two types of intensity. Let's talk about them real quickly. I'm going to write them up here. So we'll say intensity. There's two types. There's intensity, and we'll start here. There's intensity and there's sound intensity, and they are two different things, but they are related, and we can mathematically calculate both of them. So let's recap. We had waves. We're talking about waves, and you know that there's a wave mechanics like this, but remember when I talked about sound waves and how it was a little bit more like this in its orientation. So you have your molecules in the air, and then you push them somehow, and they bounce against each other with these rarefactions, which are this component, right? The non-dense, you could think of air molecules, and you have the compressions, which are the other areas that are much more dense. So let's talk more about sound here, just for a second. So let's say we had. All right, well, hold on. Let's start here. What is intensity? Let's define intensity. Intensity is energy per second. Energy transferred in a second. And you know the unit of energy is going to be our joules. Okay? But we know that we could say this too. We could say this is power, which we did earlier in the year. Power per area. And this is going to be the average power per area. So let me show you what I mean. So let's say this spot right here is the source of sound. Okay, so it's going to emit sound, a frequency from this central point here. And sound is interesting because it doesn't work like other waves do. In three-dimensional space, it will go ahead and from every direction, the sound will travel from the center point. Okay, so in three-dimensional space is going from the center point. It's making sound. If you are anywhere around it in this circle, you will hear this sound, right? And the question we want to answer really is, how can we calculate it? How does it work? How much will I hear, right? Can I hear it depending on how loud it is? And we're gonna talk about that. So let's begin. Let's say that this is on this x here. Say this x is going to be 10 joules of energy, of sound energy, okay? 10 joules. Let's rewrite this over here. Let's go 10 joules of sound energy. Okay, so let's conceptualize this. And the reason we're doing this, I could just give you a formula. You could use it to calculate whatever you wanted. However, I would like to really discuss what we're actually talking about, as you know. So let's say 10 joules of sound energy. So as it goes from this central point, it's going to, so this ring, let's pretend I'm going to do it in red. So this ring, this inner ring right here, the whole thing must have 10 joules of sound energy for the entire ring. Okay? So that's how much energy per second is going for this ring. So as it goes to this ring, it will spread out. So there'll still be 10 joules. So there's 10 joules for this ring right here. There's 10 joules for this ring right here, this ring right here, and then finally the source of the sound, okay? So that means that as it goes out, let's say this half will be 5 joules, and this half would be 5 joules of sound energy, amounting and adding up to our total 10. But that also means that if we took half of this half of this outer ring would be 5 joules, and then this half would be 5 joules, resulting in the 10. So as it goes out and out and out into the molecules of space, it is spreading out. It is the same intensity because energy has to go somewhere, right? But it will be in these, it'll be distributed the farther and farther it goes. So this means if you took this little chunk, if you said, okay, I'm right here, I'm standing right here, this far away from the source, what will I hear, right? Well, you're going to hear a fraction of the 10. You're going to hear everything that is not this, whatever's left over, you'll hear this little tiny bit. Okay, and so naturally, if the farther out you go, if you're over here, or you're over here, or you're over here, it's going to be a smaller fraction of the sound. And if you're up here, right, the total area of the sound is less, so you'll hear more of it. And I hope that makes some sense in terms of how the sound is being distributed. Power per area, okay? So as the area gets bigger, right, the implications, look at the formula, things are going to be happening. So remember, and I'll write that here for you. Let's make sure you get that on your notes, that I'll do this. I'll say this is 5 joules of sound energy. So is this. Write it right there on top of that guy. Boom. And then this half is also 5 joules. Okay. So we're just moving the molecules. Whoa, 5 joules. Hopefully that makes a little bit of sense in terms of how we're going to measure this stuff. So let's talk a little bit more about this. So since it is in three-dimensional space and time, it travels in all these directions. We can take cross-sectional areas. We can do some nifty things with it. But let's talk about these units because we have energy per second is power per area. Let's think about that for a second here. So area in this case for our example and our thought experiment and how you should think about it is 4 pi radius squared, right? And that should make some sense to you from geometry. So I believe if we take power, which is in watts, right? And I'm going to run through some little thought experiments for you here. But if you take this area and you plug it in here and you have the equation for power, which will be watts per meter squared here, you'll have your formula that you can use for your worksheet, the bookwork today. That is on page 415, 1 through 5. I'll write that over here. Page 415, 1 through 5. I believe this equation, if you plug this in, this right here, and it is stated in your textbook on those pages. This, in combination with this, that will be your equation that you're going to use for those basic problems. However, I want to talk a little bit more because that's interesting. We know that we know what power is, we know what area is, we know that there's going to be a certain amount of things passing by a certain time for a certain area. However, I want to talk about the decibel scale a little bit. So let's see, how should I do this? Okay, so that is intensity. Let's not get it confused with sound intensity. I'm going to write that here. Sound intensity, because intensity, if you noticed, was a measure of what? Well, it was joules, right? We said sound energy. Sound intensity is something that humans use to calculate. Really, it's just how loud something is. So how loud is it? And so it's a much easier way to conceptualize when we use this. And if you've ever heard of a decibel or the decibel system, that is what we're going to be discussing. And so it is in measured in decibels, notated little lowercase d, capital B, because it is a prefix. I'll tell you why we don't just call it the bell system and we call it the decibel system in just a minute. Let's give it to you. Let's say formula time. Let me move my notes. I am so short. Cannot see them. I need a virtual step stool. That's what I need. All right. So a decibel, you'll see it notated different ways, I think, but we will just use dB. I think you'll see like beta, maybe. There's different Greek symbols, but for our purposes, this is fine. Decibels equal, so the number of decibels, you could say, number of decibels is equal to 10 log, and this is log base 10, not the natural log of the intensity divided by, and this is a weird variable. I'm going to give it to you. This is 10 to the negative 12th. 10 to the negative 12th watts per meters squared. Now, let me break this formula down for you because I know it can get a little funky. Might be intimidating at first. I promise you it is not. And the textbook doesn't have logarithm calculations for decibels, which I found disappointing. So I will probably have a worksheet for you of some kind. And if not, well, I think this still will help you in your understanding of the decibel system. I feel like it's strange to talk about sound intensity without really going into the decibel system and how what it means to have the threshold of pain and what kind of sound and magnitude we're talking about. So we'll go over it even if we don't formally quiz on it. So we know a couple things. We know what a decibel is now. We know this is log base 10. You know this. I'm going to go over briefly what logs are in a second here. Intensity. Well, we just defined intensity, did we not? So intensity is going to be power per area or watts per meters squared, just like our denominator in the parentheses. So this is the intensity of the sound, okay? So let's say, and what this value is, this guy right here, 10 to the negative 12th watts per meter squared. This is the coolest number. This is the threshold. Threshold, is that right? The threshold of human hearing. So this is the quietest sound we could ever hear. It's a trillionth of a joule per second. So if you picture a joule passing by 1 meter squared per second, this is a trillionth of that. So our ears are insanely sensitive to sound. We can hear very, very well, and that's not even, and humans can't, you're aware, our senses, our ears especially, are not quite as strong as other animals. However, when we talk about the actual energy being transferred, we can hear energy being transferred through matter. It is very, very cool. So, and I'll say it again, 1 trillionth of a joule per second we can hear. We can physically hear that. And so if you picture literally, let's do this. You picture 1 meter squared in a box, right? And you have waves passing by your box. If this is, and so a watt is 1 joule per second, right? Joule per second. We can hear this 1 joule per second passing through this very, very easily. It's quite neat how sensitive our ears are. But anyway, enough about that. So this is the smallest thing that we can hear. If we take it and we draw a scale with it, for human threshold of ears, 10 to the negative 12 watts per meter squared is the very end, or the very bottom of where we can hear. So this would be the faintest thing in the universe that you could potentially fathom. And then up here at physical pain, and of course there is no limit, right? You can hear very, very loud sounds. It's called blowing your ears out with your headphones and other things, going to concerts, getting ear damage. This would be the threshold for pain here, where it's not going to be good. You're not going to be wanting to spend very much time there. Very, very painful. So with that, let me go over what this logarithm scale is and give you an example problem for this. So really, but all you need to do is know that this is a constant, right? This threshold for hearing for humans, 10 to the negative 12th watts per meter squared. That's a constant. You can keep that in mind. You'll always use that for the denominator here. But the intensity you'll be given, and then you can just plug it in. I don't think it's too complicated as long as you know a little bit about logarithms. Or I could give you the decibels and say, hey, what's the intensity of the sound coming from those decimals? Coming from the decibels, right? So let's quickly review logarithms very briefly, because I know, hopefully, most of you know them. Logarithms, very quickly. Logarithms. Logarithms are a fancy way that physicists and chemists use as a notation to turn very big numbers into very small numbers. It's kind of like an extension on scientific notation versus regular notation. So let's think about it. So if you have the log of, and these are all going to be in base 10, I'll write it here, log base 10 of 100,000. Okay, so 100,000, pretty big number. We don't want to be typing this into our calculator all the time. We don't want to have to deal with this forever. So what is this equal to? So it's saying, all logarithms are saying is that, okay, this 10 right here, this guy, whatever the log base is, in your case, and in decibel cases, it'll always be 10. It says, hey, what it looks at this guy in the parentheses, and it says, to what power must I raise myself to equal this value in the parentheses? Okay, so 10 to the what is equal to 100,000. That's really what this is asking. And so let's see, 10 to the what is equal to this. And that's all this expression is saying. So we could take log base 10 of 100,000, and we can go ahead and call it 5. All right, because 10 to the 5th is equal to 100,000. And that's all these are saying, okay? So let's go ahead, look at one more briefly. What about the log? And if you don't see the number after the log, that means it is log base 10. Keep that in mind. What about a billion? 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3. Really don't want to be typing that out into your calculator. Well, what power must I have to raise 10 to get to a billion? So this would come out to be 9. So instead of writing log base 10 of a billion, we can write the number 9, and it means the same thing in this case. So one more thing to talk about why it's called the decibel system. It is not called the decibel system because it is log base 10. It is called decimal, well, it's one of the reasons, but it's also called the decibel system because of this guy right here. You know the formula, number of decibels equals 10 times the log of base 10 of what we're dealing with. So it's this that's doing it. If this 10 did not exist, this would be the Bell system, not the decibel system. So we could take these really, really hard numbers and condense them down into the decibel system, which is rather neat. All right, let's do an example problem, shall we? Let's move my notes, and we are almost done here. Hope you're enjoying this as much as I am. Whoops. All right. All right, perfect example. Ben Carroll's standing right here. Ben Carroll's standing right here. And he has his calculator and has buttons on it. And he's getting frustrated because he doesn't understand how to input his parentheses. And so he is going to yell across my classroom profanities at, you guessed it, Mr. Cameron Tallis, who is standing here, a little bit happier than Ben Carroll, probably laughing at him, ha ha ha, with his calculator. And his calculator is right there. So let's say that Ben Carroll's yelling, and he is yelling at an intensity of 10 to the negative 5th watts per meter squared. So safe to say Ben's pretty angry right now. It's pretty loud, rather loud. So the question is, okay, how many decibels is Ben screaming at? Let's declare our ignorance. How many decibels is he screaming at? Or sure. So let's plug it into our equation. So we could say we know the equation, decibels, number of decibels equal to 10 log 10 log base 10 of our intensity in which Ben is yelling. 10 to the negative fifth. And I'm going to leave out the units, watts per meter squared. You know they'll cancel out. 10 to the negative fifth, followed by always the 10 to the negative 12th threshold in which we can hear as human beings. And it'd be interesting to do this scale an equivalent decibel scale, say, for like dogs, because then this value would be completely different, right? The threshold value would be different. So then the decibels would change if you're in dog decibel system. I don't think that exists. Go ahead and Google it for me. Get back to me on it. Alrighty. So what we can do next, you're going to have to know a little bit about logarithms. However, this will equal 10 log. We can simplify it a little bit. 10 log of 10 to the 7th. And if you need more logarithm rule help, you can consult Khan Academy about them. I'm no math teacher, but I do try. If you do if you do this in your calculator, you will get, if you do log, this guy right here, let me change colors. If you do this guy right here, you will get 7. And wonderful. You are left with this. You're left with colors. You are left with 10 times 7, which is 70. Ben is screaming at 70 decibels. Which is fairly loud. I think typical conversation is 60 to 65 decibels. However, you remember it is logarithmic in the scale, so as you go up, it is not, how do you say this? It is not linear. It's a logarithmic scale, so it goes up, logarithmically, I guess would be the term to say. So, again, that was one example problem. You will not be using this decibel notation or calculation yet, but you will be using, like I mentioned, you will be using the intensity equation, this guy right here. It's also in your textbook. Make sure to do page 415, 1 through 5. I will upload your answers for you tomorrow and have more work on the decibel system. I hope you learned something about sound. Ben Carroll, stop screaming in my classroom. I hope this was helpful. I will see you guys next time. Thanks for doing science.